Here's 2 pieces of good advice. Number 1, switch to Geico and you could save hundreds. Number 2, never tell your mother-in-law she can stay as long as she wants.
Well, tip the man.
Geico. Call or click today to see how much you could save.
Hundreds. Number 2, never tell your mother-in-law she can stay as long as she wants.
Well, tip the man.
Number 2.
Okay, this is going fully recursive. I guess I'm just going to go here. God. Can anyone hear me? I'm in an incognito mode window, so I can't even frickin' log in and actually type stuff, which is unfortunate. Hey there. Let me just wait a bit in case people want to join. Alrighty. Let's just make sure I didn't break this code. It's a little bit slow, I guess, because of the asserts. Oh, hey, James. I guess you can watch the archive later, although then you lose the ability to ask me kind of heckler questions about what the fuck is up with my code. Sweet. All right. I guess I'll get started. I guess other people can watch the archive later. So yeah, I posted this, not really a toy implementation, but sort of a fairly minimal implementation of basically the dictionary operations you need. So find, insert, delete, and my actual implementation has some additional stuff. But that's like I intentionally sort of pared down the public version. I'll post the other stuff later, but just to sort of indicate what the real meat and bones of this thing is and how compact and simple it can be. So the reason I started working on this is I was working on my stupid text editor that I was streaming the other day, and I got to the point where I started to need some sort of ordered data structure for doing range queries. So, for example, if you have like a 10 megabyte document, like source code maybe, and you have all these intervals to store, like in Visual Studio, there's syntax highlighting, and it has to somehow store data about what intervals of text have which visual properties that you want to render on the screen. And obviously, you can do something like a sorted array for that. There's various data structure choices, but some sort of ordered search tree is obviously sort of first in line. That's like a obvious candidate. And I have like an allergic reaction to all the standard binary search trees, like the balanced variants, like red-black trees or AVL trees. For some reason, even the simpler variants like AA trees and left-leaning RB trees and all that stuff. I always thought the invariants for them were sort of completely magical. Like the red-black invariant is kind of crazy just in the face of it. And it turns out, I believe, they were actually discovered by distilling down the B-tree invariant to something that didn't refer to anything related to B-trees, which kind of explains it, why it's so arbitrary. But anyway, the B-tree invariant for me has always been completely obvious. And the whole idea of this sort of factor of two merging splitting thing is also something that recurs in other data structures. So for some reason, with a bit of work, just with a basic invariant, I've always been able to figure out how to implement it in a working way fairly simply. Whereas with the red-black trees and AVL trees, and I guess even, what's that stupid amortized 6ec thing? Splay trees. Like those, I always have a hard time getting right. Pretty much the only standard binary search tree I can write in my sleep is like the, what's it called? Trie, where you use a random heap key to create some balance. But anyway. So yeah, B trees. I've always liked B trees, and I thought I would do a new implementation for this. Let's see what Wikipedia says. Yeah, like Sean is saying that RB tree is just a 2-3-4 tree, and AA tree is 2-3 tree. Let's see what Wikipedia says about B trees because I don't want to draw too many diagrams. Yeah. B tree. Let's see if there's a B plus tree. What I have is technically a B plus tree, but I mean, a B plus tree is what everyone calls a B tree, pretty much, because I don't think B trees are actually commonly used, like the true kind of B tree. So B plus tree is a standard type. The idea behind a B plus tree is, I mean, first off, rather than having, say, binary fan out, you have some variable fan out up to a maximum limit. And unlike a normal B tree, a B plus tree distinguishes internal and external nodes, aka leaves. So internal nodes that are not at the leaf level, essentially only their only reason for existing is to divide up the key space. And then all the payload, the actual values of the key value associations live in the leaves, and that makes things simpler in a few ways. I'll maybe go over as I walk through the code. Yeah. But yeah, let me write down some of the basic invariants. I actually think I have them throughout my code. One thing I didn't include, I have a few inline invariants in the functions themselves, but the big thing I actually wrote to get the correctness right, which is not in the code I posted, is are like data structure invariants that are not like per node or some local version, but are kind of like require you to traverse the entire tree. Alex is asking, what about B star and AVL trees? I think AVL trees are still used. In fact, on Linux, there's a standard library called libavl, I believe, which is used pretty much in every software. I mean, that's an exaggeration, but like libavl is used all over the place. So I would actually expect that through libavl, AVL trees are in very wide use. B star tree. I can't remember what the difference between B plus and B star. N-word tree with a variable, but often not consists of. Okay, that's definitely not that. It doesn't even seem there's a B star tree here. Oh. B star balances more neighboring internal nodes to keep the internal more densely packed. I see. I gotcha. All right. But yeah, let me just go over the data structure invariants, because I've actually encoded them as executable code that I use to catch mistakes during development. So first off, one basic fact about the way the data structure is set up is that a node pointer itself doesn't actually know whether it's an internal node or an external node. And the reason that works is that, and maybe I'll try to indicate why that is later, but B trees have this magical property that, unlike binary trees especially, you can actually have all the leaves at the same level. So just looking at the actual nodes vertically, they are all at the same height. And the reason for that is B trees basically grow horizontally by default and only grow vertically quite rarely. And so even though, for a binary tree, if someone requires strict balance for a binary tree, then it has to, like the number of keys has to be very specific. For example, if it's a leafy tree, it has to be like 2 to the n size elements. I guess it would be 2 to the n minus 1 if there's interior nodes. But basically, for a binary tree, strict balance is impossible. For a B tree, or something like a B tree, like an n-ary tree, where you can compress the node size as you want. Perfect balance at the vertical level is completely trivial. I mean, it sort of falls out, but you can see it's easy to achieve. And really, the more interesting fact is like horizontal balance, if you will. But it turns out that you can get the same logarithmic time guarantees with a B tree if you can guarantee that the horizontal balance is never too bad. And there has to be at least one element in each leaf, and then you can guarantee the usual logarithmic search time where the log is of the number of elements. But anyway, so but yeah, so the nodes themselves don't actually know their height. That's only stored in the tree descriptor, and the tree descriptor basically consists of the root and the height. And so as the height increases, this thing increments, and then when you traverse down the tree, you can figure out when you actually hit the leaf level. But anyway, let's look at the invariants. Most of the invariants are actually standard search tree invariants, which is from the tree level, from the overall tree level, you pass down the min-max key range, which starts out as the entire key range. So my keys are 32-bit uints, and so it goes from 0 to uint 32 max. And then as you traverse down the tree, you basically cut up the key range, starting with this min-max range that's passed in from the caller, and then as you each of the keys of the node basically define these half-open intervals. So if you are in a context where min key is sort of your enclosing min key, then the invariant, well, let's see. The interior key invariant is like key, let's see, key 1 is less than key 2 is less than key 3 is less than max key, and then min key. So that's like the standard key invariant, and that's really all you're checking here. And so even though this is really just almost like a definition of a search tree encoded as a bunch of recursive invariants, this thing by itself was actually like enough to catch basically all my bugs. But yeah, I wanted to go over some of the operations. The first is just to point out that the B tree find is like any other search tree find. It's not that different from doing it on binary search trees. You traverse down, you walk down the tree doing binary searches of the key, of the keys within each node, until you hit the leaf level. And in that case, if you actually found the key you were looking for, then you return a pointer to that. Otherwise, you return null. And so, the search is completely trivial. The one that's non-trivial is actually the insert. I mentioned how all B trees are perfectly balanced height-wise. But widthwise, there is an upper bound on how big the nodes can get, and that's the constant I call Bmax here. And so if any time, so first off, insertions always happen initially at the leaf level because the data can only live in the leaves. So eventually you make your way to a leaf and you're inserting a key and a value. First we check, first we find the index where that key falls. If there's an existing slot there that matches the key we're inserting, then we just override the existing key because this is not like a multi-map. This is a that can only have one key instance. Otherwise, well, in the common case, we actually just do a normal array insert. So this is like an assorted array insert of the key and value. And if you look at this macro, it's just a standard move memory to move things over by one and then assign to it. So in the common case, we just do that. The case where we can't do that is when the leaf capacity is already maxed out. And if the leaf capacity is maxed out, this is where sort of the B-tree splitting magic happens. So suppose, for example, we have a node of size 32, or Bmax is 32, and we've inserted stuff into a leaf, and it's now size, and it's already size 32. So if we inserted the next element, we would now require storage for 33 elements, but we don't have that. So the idea here is actually really simple, which is you just take the existing size 32 leaf, and you split it into two leaves that are each responsible for 1/2 of the existing key range. And so you create this thing, new sibling. It has size bmin. Bmin is exactly half of Bmax. So it has size bmin, and you can see I offset the keys and the values pointers by bmin so that it grabs the second half of the existing element range. I then shrink the current leaf. So this new sibling is again like it's my right sibling. It's not my, or it's my greater than sibling, not my lesser than or left sibling. So I shrink myself, and then we have to find out the key index, whether it fell into the old range or the new range. And if it's in the new range, then we have to continue with the array insertion in that new sibling and then offset the index accordingly. So this is actually pretty simple. So B-tree leaf insertion contains most of the essential ideas of the overall data structure, but it's a little bit simpler than the interior node case. So you'll note what it does here is when it creates a new sibling, it returns it to the caller. And so the idea is that when an interior node is doing an insertion into a leaf and the leaf returns something, it can then insert the sibling next to the original child in the appropriate space. So we can see that here in the node insert. I'll make one footnote, which is special to B+ trees. In a B+ tree, so look at this here. When you do this key search to find out where the key to be inserted falls in relative to the current node keys, if you get an index equal to node length, that means that the key is greater than any element in the keys array. In that case, what we do is we basically enlarge the final key range to enclose the key to be inserted. So I think this is not the same for B trees. For B trees, the final key range goes like implicitly up to plus infinity. But with B+ trees, or at least the way I do B+ trees, you have to always like enlarge the final key range to enclose the thing to be inserted if it falls off the existing key range. Anyway, so this does that. So at this point we have a valid index because we did this decrement. Then we just do a recursive insert. And in the process of doing a recursive insert, the existing node we inserted into, the existing child we inserted into, may be split and get a new child from that. And then basically once we know we have to handle, like once a new child was produced, in the common case as with the leaf insert, we can just do an array insert and call it a day. The one thing that's a little different is that we have to update the key ranges to reflect the new split. But if we try to do the insert and the node is already full, we basically do the exact same thing we did for leaves. But yeah. So far what you'll note is that the nodes grow horizontally by default, which is what this array insert does. If they get full, then they don't grow vertically in place. They just produce a new a new sibling essentially, and then it kicks the can down the road, lets the parent figure out what to do with that new sibling. And the parent will generally try to do its own horizontal growth to accommodate the sibling slot. But that may not be possible. So sometimes, although very rarely, you will have cascades of kind of overflow conditions that percolate up the call tree. And so this is where we get the only case where vertical growth can happen, which is at the very, very root. So if we go to the initial entry point function called btree insert, you can see that it defers, it just normally starts by deferring the insert to the root node. And if in the process of doing that insert into the root node gets a new sibling, then we actually have to create a new root node, which will have two children corresponding to the old root and this new root sibling. So you'll note, like if you look for where height is incremented in the file, it only happens in btree insert. So the only case where vertical growth happens in the tree structure is actually at the very, very root level. Everything else is just horizontal growth. Does that make sense so far? One thing I wanted to talk about is deletion. The way I do deletion is actually way, way, way simpler than insertion. Traditionally, insertion is sort of the quote-unquote easy case, and deletion is left as an exercise to the reader. And I remember the first algorithm book I had was, what is it, CLR textbook? I guess it's CLRS now. This big Introduction to Algorithms book, which is this like 1,200-page monster. And once upon a time, as a teenager, I wanted to figure out how B-trees work and implement one for some code I was writing. And I went there, and I'm like, oh, they have pseudocode for B-tree insertion. Just pseudocode, of course. But then they left the B-tree deletion as an exercise to the reader. And B-tree to deletion, I think, is notoriously difficult to get right, at least in the classical textbook variant. And so that was a bit of a dick move, actually. But it turns out that there's actually a way to do B-tree deletion, which is actually the way that I learned later is the way that almost all practical database systems that use B-trees do it, which is now called relaxed deletion. And the idea is basically deletion can never shrink the tree vertically. But what it can do, and in the process, it will have to sometimes let leaves become empty. But it never actually shrinks the height. Now this seems really bad, and from a space utilization perspective, it can be pretty bad. I should note that I do have one thing I do, which is not strictly required, but it does help, and it's something you can do without breaking the height invariance. If a node has, like, say 10 empty leaves, it can delete all but one of those empty leaves. It has to leave the one left over, even if it's empty, just to preserve the height invariant. But it can delete everything else. So this is actually just an optimization. In theory, you wouldn't need to do this, but it's like, you're already being a little bit sloppy or relaxed, if you will, with the deletion with this approach. And so deleting what you can without breaking the invariant is sort of a minimum effort attempt at doing something. But basically the idea is that, obviously a delete at the leaf level is just like an array delete, so there's nothing to it. And it just returns to the caller of whether it became empty. And then, like I said, if you're a node, if you delete in a leaf and that leaf becomes empty, if you have more other children, then you can just delete it, and there's no worry because you still have the right height and stuff. Oh yeah, so the thing I wanted to talk about was basically like why this is quote-unquote valid. It's obviously correct, and in fact, you can see that, this code is almost the same amount of code as the B-tree find. Like, it's very little code. It's much simpler, and both in terms of lines of code and conceptual simplicity than the insertion. So what's the validation for this? Like, why doesn't this go worst case linear time on operations, basically? And that's what I wanted to talk about. Now, the interesting fact about this is relaxed deletion. Maybe Fabian remembers the name of this paper. Relaxed deletion in multi-way search trees. Deletion without rebalancing in multi-way search trees. Let's see here. Is this the Sen paper? Who wrote this? Is this Tarjan? And maybe it's not the one I'm thinking of. Why is there no author? What the fuck? Oh yeah, I guess it is Sen. Yeah. All right. I mean, you can go read this paper if you're interested, but they basically talked about this notion of deletion without rebalancing or relaxed deletion. The other one, I think the one I thought of was relaxed deletion in binary search trees. Yeah, this one. Let's see. Yeah, so there's a little anecdote at the beginning, which I think sets the stage in a nice way. So there's a database provider who's contracted to build a database, and they used a red-black tree, but they only did rebalancing after insertions, not deletions. And it turns out that that doesn't work. And so the question is, why does it work for B trees? Because, I don't know if they mentioned that, because the very interesting fact is that if you go, like I actually have the book on my shelf right here. Let me see if I can find it. You can't see it, but maybe I can find it. If you open up your trusty copy of Gray and Reuter Transaction Processing, which is like the classic book on database management systems, and if you go to the page on if you go to the page on B trees, probably in the back somewhere. B trees system restart. Okay, I'm not gonna try to find it right now. But if you go and read the chapter or the section on B trees, what they mention is they basically talk about this problem of B tree deletion. And what they mention is that it's been found in practice that it's actually not worth it, even for performance reasons, to do the more complex balanced or like rebalancing. The problem with, I'm not going to go into the algorithm too much, but the classic B tree deletion algorithm requires you to do merges up the tree once nodes become underfilled. The problem with doing that is that the neighbors may not be small enough that you can do that merge. And so just in order to do a merge, you may have to do further splitting. And so you can already see why, I mean, aside from being complex, it's also inefficient because you can have a cascade, and in fact, it happens more than you'd think. Unless you make the lower bound really small, if you make the lower bound like, half of the max, then you end up with a lot of cascading merges and splits just to accomplish a single merge. So the classic algorithm, aside from being really complex in terms of the invariants you have to maintain and getting it all right, is actually slower in practice. I mean, that's what all these database people found. And trust me, it's not because they don't know how to implement it, right? Like they actually tried it and they ended up going with a simpler relaxed deletion algorithm. So that was an empirical fact for a long time. And this was used in database systems, which, if anything, are subject to denial of service attacks. So if there was a way to elicit a worst case behavior in some fairly easy way, I'm pretty sure it would have been found. So fast forward like 20, 30 years, and there's this series of papers by Sen and Tarjan, and I don't know if they restarted the inquiry or if they're just continuing it. I don't know the literature about this stuff that well. But basically, they started trying to get theoretical grounding for why these algorithms, why this relaxed deletion algorithm works as well as it does in practice. And in the process, they managed to extract basically a worst case guarantee. But the worst case guarantee, rather than being logarithmic in the number of live elements in the tree, is logarithmic in the number of insert operations. So I think one way you can kind of intuitively see that is that suppose you have a B tree that's used in two discrete phases. So phase one, we do like 1 million inserts, and then we do 1 million deletes. So after that, semantically, the tree is empty. But because we're not doing merges, the tree still has all this leftover structure. There's nothing in the leaves, but the interior nodes are still splitting up the key space based on the original key distribution. So now suppose we have a phase two. In phase two, we do another 1 million insertions, but now the insertion keys are completely disjoint from the original key range. So for example, maybe the original key range was 0 to 10 million, and maybe the second key range, or the key range for the second insertion phase is like over 100 million exclusively. So you can see why things are still fast in that case, even though we have all this junk hanging off to the left, which is essentially the entire subtree that originated from the phase 1 insertion pass. We will now get a right subtree corresponding to the new key range. And so basically all we're paying when we're searching the new keys distribution is we have to walk past, well, and that's even a worse case. But like there's basically like an extra key range on the left that you have to go over. But at most that adds like one extra step down the tree. And so if you think about that, you get that log bound on the number of operations, not the number of live elements. So anyway, that's I think they proved that, and then there's also a bunch of follow-up work about how to make it work in more general cases. And specifically in the case of this paper, which is pretty interesting, they have this anecdote in the beginning of where someone applied this approach naively to a red-black tree, and it didn't work. They figured out, well, how can you actually make it work? Because there is a way to make it work. And for AVL trees, they came up with this thing called a relaxed AVL tree, or a RAVL for short. And that's sort of the same idea. Like, how do you make this balance or a relaxed deletion actually work for plain old binary search trees like AVL trees? All right, I think that's enough blabber for now. I wanted, oh yeah, one thing I didn't show in the code I posted online, but it's like another 50 lines of code, is how to do iterators, and you need these for you need these if you're doing range queries, which is actually what I'm going to be using this data structure for once I use it in my text editor. The typical thing you do with range queries is you find the iterator corresponding to the beginning of the key range, then you find the iterator corresponding to the end of the key range, and then you step the initial iterator until it reaches the end. And it's also just useful if you want to iterate over all the elements in the tree, which is obviously a trivial case. So that's like 50 lines of code. If you guys have ever written these things before where you have to write tree iterators, it's surprisingly painful because unlike when you're doing just a plain old recursive traversal of a tree, you have to manually keep track of the path you went down the tree. There's no implicit program counter and call stack to track that shit for you. So you have to sort of reify all that state and figure out what the invariants are and manage it correctly. And so I'm not going to go over it here, but I mean, this is essentially emulating what the recursive traversal is doing, which is walking up and down the tree based on the state of the iterator. And so I'll show you what that code looks like in practice. But yeah, like if you want to do an end-to-end traversal, you start with an iterator. You say find first on the iterator and the tree to initialize it. So now it points to the first leaf, or the first key value pair conceptually, but actually physically it points to the first element of the first leaf, the first non-empty leaf, I should say, because leaves can become empty as we've talked about. And then you can get the key and the value. You can step next, and you can check whether it's done. By checking this hasNext member field. All I'm doing in this snippet of code, by the way, is I'm generating a bunch of random entries, and then I'm verifying that the sorted order of those entries matches the traversal of the B tree using this iterator. All right, people are starting to ask questions. Let me just catch up. Yeah, Sean, I know that it's super trivial with parent pointers. I mean, yeah, that's like I probably should do parent pointers, but yeah, I think that's perfectly valid. With parent pointers, it is much easier. Although I want to point out something interesting, an advantage of this approach. So maybe I'll pose this as a question. If I give you and there's different ways of doing this, I guess. There's different valid answers. If I give you two iterators into the same tree, how can I see whether one comes before the other? Like the ordering, the ordering within the tree. How can I just compare two iterators like that? So I guess there's too much stream delay for me to just fill up the dead hour waiting for that. But I guess I'll give away the answer. There's different answers depending on how you do things. But if you have this path representation, what I realized, and I actually think I used this once upon a time in BSP trees when people were doing key, or like I think it's in Abrash's one of our Abrash's articles about BSP sorting keys, which is if you have the path, if you have an element. Oh, Sean, actually that's right. That's a really bad answer I had there. What the fuck? What am I thinking of? Yeah, I guess in that case it really does. Okay, that's really stupid. Yeah, I'm just going to pretend I didn't say that. What I was going to say is that if you didn't have the keys to directly compare, which you do, then you can basically treat the indices on the path up to the root, actually the path down from the root to the key, as a lexicographic sorting key. And I think that's what I remember from. Yeah, I guess that's also true. Although the algorithm I'm just describing takes time linear in the number of in the path length, so it's not great either. Although it's like 6. I guess it could be 6 bytes. I'm using 32-bit ints to represent indices, but for a B tree with a good fan out, the path is the height is never going to be more than like 5 or 6, and so you could use bytes easily to represent. Oh, that doesn't make. Sorry, you could use bytes to represent the fan out, which means you can store this index in a byte, and then that times 4 or 5, 5 or 6. So it's like 6 byte compares, I guess, for the lexicographic comparison. Yeah, I can see that being useful for big opaque things. Problem for STD map replacement is, yeah, the STD map thing is insane. I think it was also you, Fabian, or maybe it was someone else who pointed out to me that even with the unordered map, they have these weird semantic requirements on stability. Actually, not stability of the iterator in the hash map case, but stability of the actual like element reference. That it has to be stable over time, which means that you can't do the simplest kinds of open addressed hash tables, which is, I mean, that's my go-to. If you guys don't know, this is 200 lines of code. I'm trying to remember. Yeah. So like a simple addressed open address hash table like this. It's simple. I think it has a really this kind of simple open address table has a great weight to power ratio. But apparently it's not usable for STD unordered map because of standard people. I don't know if it was a backwards compatibility thing where the old, maybe they found they wanted to replace existing STD hash map usage with STD unordered map, and they found that there's too many programs that relied on the old behavior. And the old behavior is something you get kind of for free if you're doing external chaining. But anyway, yeah. So that's pretty stupid. But yeah, if you guys don't know about Sean's hash table, that's a kind of a nice, simple drop-in data structure. It was actually sort of my inspiration for this code I wrote, which is like I should be able to do something that does basically what I want in like 200 lines of code. For a good weight to power ratio. That doesn't mean you can't go crazy with the optimizations and stuff, right? But you should be able to do something clean but still efficient in that amount of code. Okay, I should mention something about benchmarks. I have like the shittiest benchmark data. Like I wasn't planning on presenting this. This was just stuff I gathered myself. So please don't. I tweeted a completely preposterous number, by the way, that I quickly deleted. Although both Paul and Fabian responded to it before I could delete it, so I was awkward. I said that like I'm 20x faster, and I think I deleted it within like 30 seconds. That was because I was running in debug. So yeah, profiling stuff in debug mode, not a great idea. I don't know how many times I've made that mistake, but usually I don't tweet right after it. Usually I catch it myself before announcing to the world how awesome my code is. So in practice, though, for large maps, I'm seeing. I mean, you can see the speedups here, 3 to 4 times for large maps. Boom, boom, boom. I also have some comparisons here using linear search or binary search for the internal node search. And that has some interesting behavior that I haven't been able to totally account for. I don't think I'm going to go into that. But yeah, for like really. Oh yeah, I want to mention my other stupid benchmarking mistakes. This is also embarrassing. So when I started doing my tests on larger maps or larger number of elements, like 1 million, 10 million, whatever, I used rand to do that. So I guess people can already remember the punchline. But I was doing the same basic rand modulo range thing. But of course, rand max is like fucking 32K. So when I was generating all these elements, like once you're generating enough, almost all of them are colliding, and so you're basically not doing any. You're basically not doing any new inserts. So there's no structural changes. You're just basically overwriting them in place, which is obviously fairly fast. Yeah, yeah, Fabian got it. What am I comparing against? I'm comparing against the standard STD map, like ordered map. I actually don't know how it compares. I think last time I did wrote some hash table code to compare it against STD map, which is obviously unfair because STD map is ordered and hash table isn't. I think mine was like 8x faster, and so using that ratio, this is still pretty good. So it's like half as slow as a hash table under those conditions. That wasn't a hyper-optimized hash table. That was probably something similar to Sean's code. But anyway, that's just using the B tree as a dictionary, which is kind of I mean, not the slowest case, I guess, but it's not what it's designed for. Um, the thing it's really designed for is, well, something like this, where you spend a logarithmic amount of time to find an endpoint of a traversal interval, and then you just jam on that. And so really the thing for that is making sure this thing is reasonably fast. And probably I should use parent pointers, and I should definitely see if that's faster. It's certainly simpler, and even if it takes up a bit of storage. Very insignificant amount of storage, though, especially if you have big B-tree nodes. But anyway, but yeah, so this thing is going to be blindingly fast compared to other things. I don't know how it actually compares with stdmap. I should benchmark that, but I just wrote the iterator code this morning. I would expect it's much faster because I'm going to have mostly big array chunks, right? Like if if each node is around half full, so say 16 elements, then I'm gonna do linear traversals of 16 element chunks without any random access, and so that's hard to beat when you're using a binary tree that's just doing pointer chasing all over the place. Blast out 64 elements at a time rather than classic iterator. That's a really good idea. That's a really, really good idea, Sean. Oh man, that's a great idea actually. Yeah, it's like get rest of node or something like that. No, that's a great idea. I see exactly what you're saying. I'll totally implement that afterwards. Because yeah, like in that case, I mean, I guess it offloads a little bit of the work to the caller, but if the caller has a way of operating, like for example, if the caller is doing like a mem copy of a range in the array, this would be great because if they get big chunks back, they can use some optimized code that works directly on that rather than going back and forth. But the find next inner loop is intentionally very cheap. So the common case of this find next loop is you do the index increment and you check whether you're done with the array. And so the common case is this first part of the short circuited condition fails, or succeeds rather, and it updates the keys and values. There's some indirection or there's some pointer arithmetic stuff to get this in there. But anyway, yeah, I think doing it in chunks would be nice. Yeah, linking things horizontally, I think, is a way to really kill the weight to power ratio of this code, because once you do horizontal linking, then holy crap, the inserts become. I mean, it's still like it's totally tractable, but it's become significantly more complicated to maintain the invariants. But yeah, I know it's common, but I don't know. Like I'm probably going to keep it. Maybe I'll keep it like this, but with parent pointers. But otherwise, do the up and down traversal. But yeah, updates are way worse. I remember at Rad. I don't know if I should talk about this. Jeff Roberts at Rad had had this C template library. It was basically just like a big parameterized header that you could include with different macros defined contextually. It was called contain.inl, and it was an AVL tree, and it was the thing that's amazing to me about that template, if you will, is that these days, I think most people hate policy-based design with C++ templates. But Jeff's code in contain.inl is actually the most extreme sports version of policy-based design I've ever seen. So for example, based on whether you define certain macros at the include site, you could optionally have parent pointers, optionally have sibling pointers, I can't even remember. It was completely ridiculous. Like, it could do everything. It was like the Swiss Army knife of crazy AVL templates. So, anyway, I thought that was interesting. All right. I think that's. I think there's something else I wanted to talk about. Oh yeah, maybe a general. Some general advice on writing code like this. While I think B-tree invariants and maintaining them during inserts are is way easier than any of the binary search trees I've studied, you're still going to make mistakes along the way. And there's like no way I've been able, like, I think this code probably, like for the core code that I posted in the gist, it probably took like 2 hours to write, maybe an hour and a half to write, and then another 3 hours to debug. Maybe not that long, because I did a bunch of other stuff that was sort of unrelated with the editor. Yeah, but it was probably pretty much like at least a 1-to-1 ratio between writing code and debugging, maybe even 2-to-1 on the debugging side. The only reason I was even able to make sense of that was using asserts, which I think is standard. Like, everyone uses asserts. But the thing for me that was really valuable was not just the sort of inline asserts that are like throughout the core code, but it was actually these separate assert functions, recursive assert functions. And the reason is, and this is like a very specific thing, I guess, but like, let me try to set a breakpoint here. I can't remember if I actually, I guess I'm, God, fucking. Okay, now we're going full retard. Okay, did I turn off asserts? Yes, I did. And that's not going to be useful because it's not in debug. Now it's going to take forever because it's 10 million elements. Okay. I guess these are all going to be really shallow because they're the first. Oh, you're killing me. This is what happens when you actually press F5 too rapidly in Visual Studio. Can you believe it? Let's hope it doesn't happen again, or it happens in a different way at least. I'll just put it here. Why is it not hitting shit now? Oh. No, but yeah, so during development when things were not always working out, and often they were not working out once things got fairly deep, right? Like it didn't happen with just pure leaves. You had to get somewhat deeper. Having these assert macros means that you have on the call stack all the good stuff. So like I guess there's not that much here. There's like a few nodes deep, but having these assert macros and being able to really see the path to the problem node and being able to sort of easily interrogate the whole context, knowing the min and max key range and the height, these are all things that are not stored directly in the node itself. So it's not something you can just check by looking at the node pointer. You really need the whole context. And not only does it pass down the context as function parameters, but it also has the whole calling context, or it has the whole tree context on the stack. So because of that, it was surprisingly easy to debug this stuff once I'd actually bothered writing out all this crap. Anyway. All right. I guess I'm pretty much done with what I want to talk about. Although I'm trying to remember if I promised to talk about something else. Why B plus trees are simpler? I mean, maybe I should say a little bit about that. I think the core reason why B plus trees and B trees, but especially B plus trees, are so much simpler for me than, and I admit it's a somewhat subjective statement, but by being forced to think about the general case, things becomes easier. So this is like one of the lessons from if you do mathematics, is that almost everything is simpler in generality. So for example, thinking about the 2, 3, 4 case is harder than thinking about the n case, or like the general case, for me at least. For example, the whole relationship between Bmax and Bmax over 2 is sort of a general relationship. But if you just see it in the context of 2, 3, 4 trees, it's easy to get lost in the special cases and think that you need to sort of think of, like, it's easy to fall into the trap of doing case analysis, which is always the absolute worst way to get a handle on anything. And so by thinking about the general case, it forces you to be more, to take a step back and think about the general patterns rather than just getting lost in the details. And then, deletion is still a bitch in the classical way, but by doing it this way, that kind of takes care of that. Stale links are bad. Okay, let me just catch up. Right. I think, yeah, Fabian is right. Like, for what it's worth, like this article by Sean that I linked earlier, the Judy arrays one, for me, though, reading that was like a seminal article because it captured a lot of, I mean, I guess stuff I already believed by the time I read it, but it really cemented it, which is like, I think this maybe makes me a bad engineer, but fundamentally one thing that makes me uninterested, right? Like, and if you have to do it as part of your job, then you're forced to it. But if I have any choice in the matter, I just don't like things that are like marginally faster at the expense of like 2x, like a lot of extra code, like just in terms of lines of code, but also just like conceptual complexity. And sometimes you have to go for more complexity to eke out performance or whatever, or extra features. But I'm just always drawn towards these like nice trade-offs, and so I'm kind of trying to keep this B tree in that sweet spot of complexity versus performance trade-offs. Anyway, we've been debating. Yeah, I'm actually, Sean. I would be curious to know if you've changed your tune on what you wrote in that Judy arrays paper. I think one of the interesting things about it, I can't remember if you mentioned it, I'm pretty sure the Judy arrays on 64-bit is still slow because they had all these weird like hard code or like these hard-coded data structure decisions that were based on like, I don't know, like a Sun Spark 32-bit machine from 99 or like something super specific like that. That's another benefit of going with something simple, is that it tends to just be more robust in the face of changing circumstances. Like the Judy array stuff is an extreme case of that, but I think it's true with other things as well. Like the more you optimize, the more, like most some optimization, a lot of optimization is about not doing dumb things and really understanding what you're doing. But a lot of the time is also just like taking advantage of circumstantial stuff that may not be relevant later. And Judy arrays, I think, are an extreme case of that. They have like, is it 30,000 lines of code? 20,000 lines of code for a dictionary data structure. Yeah. Like, I don't know. I guess for some people, some people have this mentality that if it's just a .lib or a .dll, then you don't care about whether it's a massive behemoth. But for me, that's just like, man, that's hard to stomach. Especially when, like you said, it's not actually optimal anymore, even if it ever was. The original Judy white paper as well is a fucking... This is like... this is like the most self-congratulatory bullshit paper I've ever read. This is completely insufferable to read. Weird typography, weird diagrams about the space-time trade-offs using relativity metaphors, just complete fucking bullshit. I mean, it's like there's some interesting design decisions in there in terms of choosing different nodes based on the number of keys in a given within a given range. But like, so much of this stuff is just, I don't know, is this like the most? It's a bunch of crap in my opinion. Anyway. Yeah, no, I know there's a bunch of these. Actually, there's a guy who has, is it Google Code? Is that the URL for Google Code? Hash array trie. There's a guy who's written like a crazy amount of different implementations of Google. Is it Google Code? Is it hat trie? Yeah, that's probably the one. Yeah, there's this guy who's sort of apparently really Carl Malbrain. Anyway, who's written like a million implementations of different trie style data structures. Oh God, while I'm just railing, let me. I spent some time like a few years ago going through kind of the whole range. So all these Radix tree or trie or all these kinds of data structures have this feature that rather than working directly on ordered keys, they use the sort of the tuple structure of the key space to split things out in a way that, at least at first glance, is data independent. And then a lot of these additional techniques, then instead of just leaving it purely data independent, even they leave it sort of semantically data independent, but then add some sort of node level data compression tricks effectively in order to keep things more tight in memory. So for example, if you have something, an extreme case would be something like a 256 fan-out tree, where most of the children are null, and so storing null pointers is stupid. Semantically, you still have a 256 fan-out radix tree, but physically, maybe it's stored as a sorted list of indexes and child pointers, which is much more compact in that case. Or maybe it uses an occupancy bitmap of a fixed size followed by a variable size list of child pointers. So anyway, there's this whole cottage industry of different data structure variations, which is basically what Judy arrays is. And once you start reading these papers, you realize how little, I mean, it's a little unfair, but like there's very, very little like real I don't know, real intellectual density to it. It's really like just milking all the variations for what they're worth. Like for example, this dude here who I guess came up with hat tries also came up with and he wants to sell you, this is awesome. When I tried to find this originally, he wants to sell you a copy of this PhD thesis. I'm like, Jesus Christ, dude, like you should be happy anyone's willing to read your shit. But anyway, he also has all these things called burst tries, or maybe he's not the one who invented burst tries, or hat tries are related to burst tries. Burst tries are basically using the B-tree splitting invariant together with tries. So the idea is that you have again, semantically, you have a fixed data independent subdivision of the key space, but physically you do something more clever. In this case, the physical cleverness is you grow things physically, and then once they reach a certain threshold, like in B trees, you then do what's called a burst, where you now have two nodes rather than one, or something like that. I think that's what burst tries are. I've never implemented them, but I just remember reading all this crap once upon a time. Does he refer to B trees? Burst trie. I think burst tries are also for strings, especially. Each leaf holds a set of strings. Right, and like the other thing that killed me with all this stuff I read when I was reading these papers was they would call them different names depending on whether the leaves were like arrays or hash tables. So for example, a lot of these data structures are hybrid. So for example, maybe in the interior nodes they use arrays, but then once the data set in a certain subtree becomes small enough, maybe they use a hash table or stuff like that. And all these tricks are like trivial, right? Like you can mix and match them ad infinitum. You can literally play the combinatoric games of, just combining anything with everything else. Because the nice thing about tries actually is that you can just nest them really easily. So you can use, for example, at the top level, suppose you're doing 32-bit keys. At the top level, you might do a 256 like dense split just with an array, because you assume the key distribution at that level is enough to sort of cover at least half the key space. But then once you get further down the tree, it becomes sparser and sparser, and then you just start doing something more compact but less random access. All these things are like anyone can come up with them once you get the basic idea, but apparently it's worth writing 100 papers about. Anyway, that's my my rant. Suffix trie. Yeah. I mean, honestly, I don't think you need, Gary, I don't think you need Charles's code. Like, the basic idea is really the important one, which is recursive structure is overrated, if I can call it that. Like, recursive structure is nice semantically, but when it comes to sort of like real data distributions, you often can gain a lot by using heterogeneous representations. So for example, with anything like a trie, you want some wide fan out at the top because you're going to get a good occupancy, but then lower it gets sparser, and so you use something more specialized. And so it's really easy to just look at your data distribution in practice and just make informed decisions about this stuff. Anyway. And the other nice thing about the heterogeneous approach is you can often use it for like non-growable structures. So for example, I know that Alex Evans at Media Molecule has said that one of his favorite data structures is a 2-level B tree. I don't know if he means exactly the same thing by B tree as I do, but I think the basic idea is the same, which is you have wide fan-out nodes with nice cache coherence within a node. And if you know you're never going to have more than like, I don't know, 16K elements, then it's really easy to just have a fixed topology, if you will, and have really nice unrolled code that has that with a minimal amount of indirection and like special case checks, because you know that there's like only 2 levels or whatever. So once you get the general idea behind that, you can go crazy and design data structures that are perfect for your data. Anyway. Let's see. Yeah. Yeah. Anything related to tries is super nice because there's basically no structural changes to the tree. They're all within a single node. Like I said, the structure is semantically fixed and data independent, and then at the node level, you can do compression basically. Maybe now that Fabian and Sean is here, I'll look. One of the cases that I couldn't really make a lot of sense of Was a case where stud map was, well, let's see here. I think this one. Oh, while I'm talking about like really stupid mistakes during development, at one point I made a statement on Twitter as well about binary search versus linear search. It turned out, like, actually, let me recreate the macro for your benefit. So I wonder, I mean, I'm kind of suggesting that there's a bug, but I wonder if you can guess what the bug is. You know, this compiles, right? This is great. Oh yeah, this is good stuff. So, you know, this is really smart, because if we have less than if we have 64 elements or less, or I guess this would be the opposite anyway. If we have 64 elements or less, we use linear search. Otherwise, we use binary search. It's really great. Does anyone see the problem? Oh, that's not the problem, Sean. Do you see the problem? I'm going to wait to see if anyone gets it before I reveal it. Well, so in this case, I mean, like, I was changing it dynamically, right? This is when I was testing different fan outs. Okay, the problem is Bmax is an enum. It's not a, if I had done it like this, then it would have worked, but I didn't. I use a fucking enum, which, I mean, that's my usual habit for constants, but yeah. Anyway, that was pretty amazing. But yeah, what was the one that was weird? So I did this one where I do like 64 operations. On a thing. Did I do these in a loop? I'm trying to remember what my stupid benchmark. Well, it's not really a fucking harness. It's a piece of shit. That's what it is. I wonder if the issue is I was reusing. No, I was reinitializing the tree between each run. So yeah, so I was doing a 64 random inserts, finds and deletes on an empty tree, and I was measuring the total time across whatever. How many is this? Like 1,000,000 runs. And one interesting fact was that with linear search, well, I guess it's not too surprising. The thing that I guess is surprising is with linear search, mine was significantly less efficient than std map. Now, std map, once things are constructed, I mean, this is basically a binary search, except that the memory access pattern is less coherent. But I guess maybe if that stuff is in cache, you know, it's basically as fast as an array binary search. So, I mean, I'm still faster with Appliance than using binary search. The only reason I thought this was a little bit surprising is that in other cases, same fan out, I believe, but much larger number of elements, linear is faster. Where do I have examples of that? Well, it's not true here. Oh, this is with small ones as well. Do I really not have? Okay, I guess I don't have the data, and maybe I'm actually high. Operations equals. Okay, I could have sworn that I had cases where binary was, with the same fan out, was like 10% slower than the equivalent linear search B tree. Still beating stud map, but anyway. Binary search is pathological for cases. Yeah, actually, so let me give you a challenge, because I wrote this code. I wrote some code related to. No, there's no actual question, Fabian. I think I realized I didn't actually have the data I thought I did, and I'm actually just high. So regarding pulse post on binary search is pathological for caches, here is a here's an interesting coding question in my opinion. Oh, hey Alex, I see. So that is you. Um, the so think about the difference. So let me. I think this is what Paul's post is about. So I may be repeating it. I think I probably only skimmed his post. So yeah, with binary search, it's bad. Like it's good in terms of information retrieve, like in terms of how many bits of entropy you're getting out of each query, right? Like you're cutting the key space in half with each query, but it's bad because you're kind of jumping all over the place until you get to the final slice, and then things are maybe fairly coherent. So the obvious thing to do is store an implicit level instead of sorted array. Store level ordered implicit binary tree, which would be like, I guess this key would go first, then recursively this half, and I'm just gonna what's it, 1, 2, 4, 6, 7, 8, something like this. And then you recursively do the same thing in here, so it would be like this, and then I guess 6, 5, 7, 8. So if you do, so this is basically just a permutation of this array. If you guys have ever implemented, I guess this is most commonly used in binary heaps, where you have this implicit binary tree structure where the indices let you do sort of traversal of the child-parent relationships. So you can basically, I think this is probably what Paul's post is about, which is that you can basically permute the thing to have the same data, and you're essentially doing the same comparisons, right? It's just that the data is now laid out in a different way. So here's I think this stuff is trivial, and I don't think the access pattern is necessarily better here by that much. But here's the next step, which I sketched out the code for it, but I never actually implemented it for real. So maybe you guys would like to try that. So anytime you're doing binary, it kind of sucks, right? You would like to do k-array. So for example, maybe do I have the code here? Maybe I'll show the code. I don't think the code is public. GitHub, k-array heaps, k-array heap sort. That's part of that code, but it's only one part, which uses. Okay, but anyway, I wrote a k-array heap sort rather than the normal binary heap sort, and it's like a good deal faster than plain binary heap sort. And obviously you can do that for binary heaps too. Like the standalone data structure binary heaps. But the interesting thing about binary heaps, of course, is that they have this implicit storage layout. And so my question is, well, so first off, to back up even more, why does trinary search on sorted arrays suck? It's because you would want to sample this one and this one in order to make a determination of where your query key falls. But these are so far apart in the array that they're not going to be memory coherent, and so you might as well just do binary search, right? So even though you're only eking out a little bit of extra reduction in the number of search iterations, but you're doing these incoherent memory accesses, so what the fuck? But we know that with B trees, you can do that sort of thing, but that's because all the keys are adjacent. So the question is, do the same thing I did here, like write the algorithm for that, but do it for general fan out. So do it for k-array trees, basically. Yeah, Fabian. I think I did 4 array. Actually, 8 array I believe was faster for my code. But anyway, so he actually has that in there for heap sort. Or are we talking about, like, does he talk about heap sort in here as well? Maybe I should just have read this then. It's embarrassing if he actually has exactly what I'm talking about. Enough of the preliminaries. Then show them. It doesn't look like this does k-array. k-array. Oh, he does actually. Okay, well fuck that. Then this is nothing new. Okay, so he does exactly, I guess, what I was describing, which is permuting the array in place to do be able to do coherent k-array search. Yeah. I'll read it in detail later. Okay. Well, I thought that was a... So I guess he already did it. Fuck that. Okay. Anyway, so that's not so interesting. But yeah, it's kind of a cute little problem just as a programming problem, just because it seems simple, like you're just permuting an array, and like what could be simpler than permuting an array in place? Or maybe not in place, but permuting it in any case. Did dependency from the loaded values to the next loads. Yeah, I guess that's true too. You can overlap all those operations. Yep, that makes sense. Yeah, no, that makes sense. The array heap. Yeah, no, that's exactly what I was talking about. Like, you can use a version of this for heap sort, and that's what I did, and I had an old gist. Actually, so while I posted that here, what was the... I did actually find one. So this one is interesting. David Mackay, quicksort, I believe that's where it's from. I don't know if you guys know David Mackay, but he is sort of a physicist and information theorist, has a really great book, which I would recommend. Mackay, Information Theory, Learning, and Inference. Okay, almost same order. Yeah, this is a really great book if you're interested in stuff. But he has a cool page on... let's see. Yeah. I think it's actually in here. He actually does the quicksort analysis using information theory in here. But yeah, like the idea with most of these sort of bisection type techniques, of course, you can think of them in terms of you're gaining increasing amounts of bits of entropy, or you're getting increasing bits of information about what the actual element location is. So he talks in here about how the traditional way of doing, he talks about quicksort and then heap sort. And the thing he mentions is that the basic way that heap sort works is that I believe when you delete the element on top of the heap, the way it let's see if I remember it. Yeah, you do it from creating a vacancy. The standard way, yeah. So I remember now. The standard way heap sort works is I guess you swap the rightmost leaf with the top one, and then you do the sift down to figure out where to put it. Is that right? I think that's the standard heap thing. So he proposes something different. And so he points out in this article that in terms of the number of comparisons, which is sort of like the information quality of what you're doing, most of the comparisons you're doing when you do that approach are basically super biased. So with a perfect information theoretical question with a yes-no answer should give you one bit of information. And he points out that that is extremely skewed with a standard heap approach. So he proposes this other thing, which I think is optimal in that respect, where basically, like he described it here, but you, rather than swapping things in from the rightmost leaf, and by the way, the reason things are extremely skewed is the rightmost leaf is in a part of the heap where like it has a whole chain of things, a logarithmic chain of things that are greater than it. So when you compare it to a bunch of stuff, it's likely to have a certain bias relationship with respect to them. It's likely to be, I guess, fairly small compared to something random, because it has a bunch of things that are bigger than it. So he proposes basically, rather than doing that in-place swap, which is, by the way, the standard thing that people use for deleting, if you store a set as an unordered array, the standard way that people do constant time deletions is that you swap the last element into the place and decrement the length value. So that's sort of the same trick you use in that standard heap sort. So what he proposes instead is you create effectively like a vacancy at the top of the heap, and then you bubble it down until the vacancy is at the bottom of the heap, and then we get rid of it because once it's at the bottom of the heap, we don't care. It's not the usual thing. So yeah, he has all this analysis of the actual number of sorts, The downside of this algorithm, as I found out, which I think I have here, is that it does way more data movement because you're bubbling things way more around. Anyway, so I don't know why. That was a little bit of a sidebar. I think that means I'm running out of shit to talk about. Anything else? Data invariants, other stuff. I think that's pretty much it. I'm done. Any final things people want to talk about? Wow, a lot of people. Anyone I know? Yeah, I'll check. Except that I just closed, well, I guess the window. Alex. And Darius Bacon posted some stuff. I don't know if Darius is on the stream. You guys should totally check out Radix sort. The reason Radix sort does not always work. Radix sort, and this is like my sort of wingnut theoretical perspective. Radix sort requires a tuple structure on the search space, which is the same thing you need for radix trees. So this is like, I think maybe Sean is gonna sigh that this is super theoretical. But a tuple structure, what I mean is, if you have an isomorphism between your key space and however it's ordered to a tuple structure, and the elements of the tuples are themselves have primitive comparison structure, then you can use that to recursively, well, you can recursively create data structures based on that, but you can also sort on it. So for example, standard radix sort on, well, you can do radix sorts based on bits. In that case, you decompose a 32-bit word as a 32 tuple of 1-bit elements. A more efficient radix sort is a 32-bit word as a 3 tuple of 11-bit elements. So you can see one of the essential things is that there's different isomorphisms. You don't have to choose a fixed one. Fortunately, most things have tuple structures, or you can get isomorphisms with tuple structures. But it doesn't work for, well, classic radix sort does not work for strings, for example, because they have unbounded length. So you would have to, I mean, you can do it, but it doesn't have the usual fixed constant time guarantees or whatever. How to implement radix sort in a trie. Radix sort, I mean, let's see, radix sort. The way you do radix sort is you do so using this tuple isomorphism, you use the fact that tuples are lexicographically ordered. So let's see, if and only if x is less than a, or x is equal to a, and y is less than b, and so on. So it's the typical thing. So the idea here is that if you sort on the most significant, so this means that the first entry is the most significant for ordering, and so if you first sort by that, and you use a stable sort, then once it's stabilized on the first entry, you then sort on the second one, and those subsections that are stable relative to the first element now stabilize within the second element, and then the third element, and then when you're done, you just traverse the key space, basically, rather like you traverse the resulting thing in order of key space rather than the actual values of the elements. That's sort of a weird way of looking at it, but in practice you do it by using, I guess, like counting sort on each range. So for example, if you're doing 11-bit slices, like this decomposition is pretty good because 2 to the 11 is only 2048, and so you can have a histogram counting table with this many elements times, I guess maybe you need well, I guess 4 bytes in the general case, but 2 bytes maybe if it's not that many elements, let's say 4 bytes. So this is like a reasonable amount of static storage. And so you accumulate, you first accumulate all the counts, and then you do a prefix sum of the counts in order to get the cumulative counts from the beginning of the keys up. And that then gives you the base of where that value should be inserted, and then you traverse it and just put everything into their own place in linear order, and that's counting sort. And that's a stable sort. And so you basically just do 3 passes of counting sort, and everything is good. Least significant digits first. I think you can do it. I mean, there's both for the classics binary radix sort. I think you can do it either in MSB or LSB order. The important thing is that once things are stabilized, then yeah. I believe the one where you start from the least significant bits, for me at least, it's less obvious that it's correct. Like the other one is more obvious for me. Like the one where you start with the most significant elements of the tuple corresponds to the radix tree for me, right? Which is like first you partition it. Well, it's like, I mean, let me give you an example. If I wanted to order, let's do bits. So suppose you have 4-bit words corresponding to nibbles, and this is one element, and this is another element. This comes before that, right? Like, because it has a greater significant bit. So we basically know that any elements that starts like this is going to come after everything that starts like this. Oops. And so you can just sort on that one first to separate them, and then within the sections you recursively sort. I mean, that's sort of the idea. All you need to do with most significant first and actually recursive into smaller partitions. Algorithms course. So I think the thing you'll find with the radix sort you see in algorithms courses is if you implement it as is, it's going to be pretty terrible because it works bitwise. Practical radix sorts always works on bigger chunks. Because you basically have to do, like, if with 32-bit words and bitwise and like radix 2 radix sort, you're doing 32 passes over the data. And you're technically doing twice that many because I guess with radix you can do the splitting simultaneous. With radix 2 you can do the splitting simultaneously with the counting maybe. But in general you have to first do the counting pass and then the permutation pass. So let me send you a link. Michael, what is it? Michael Hohensi. No, that's not his name. It's another guy. Stereopsis. Is that his name? Radix sort. And this is based on an older article, I guess, by Pierre Turdeman. If you look at how this works, this does 32-bit sorts as a sequence of 11-bit sections. And so you need one histogram because you're processing one range at a time. Oh, and this is nice. It does, oh, actually, it has, okay, so it does all the histograms at once, which is nice. So you only have to do the histogramming once. And then it does the prefix sums, and then it has to actually do the permutations. The nasty thing about these permutations is you can't do them in place, so you have to flip-flop between the original array and a temp array of the same size. One thing that's kind of awkward about this, by the way, is if you wanted to write to the original, depending on how many whether there's an odd or an even number of flip-flops, you're not going to end up in your original array. So then you're sort of left, which might be an awkward interface to the caller. You can see that's why he has this. Anyway, so I think this is probably a good example if you want to see like a practical, although this is probably 15 years old by now. Yep, 15 years old. But that's the basic idea for a practical radix sort. A histogram is just a table that for each value is a count of how many of those values exist in the array. So for example, suppose you have 4-bit value, or 4-bit values go from 0 to 16. Entry 5 in that histogram table is the number of times that 5 occurs in the array. Oh, the link. It's on Stereopsis, and then Radix, stereopsis.com/radix.html. This website has a bunch of good stuff. This is really old, but if you want to do like optimization back in the day, this was like in the early 2000s, late 90s. This had like so much good stuff back when MMX was a thing. As for tries are super easy to implement if you just want to do the vanilla version. Some of his ideas are underinformed. I think that's a true statement, John, for pretty much anyone. I think a lot of my ideas are underinformed, and maybe even a few of your ideas are underinformed. Let's see. Are people starting to get bored? Okay, what is this? Oh, that's the Darius Bacon one. So I don't know if Darius is watching. I actually have an earlier, let's see. I have an earlier Python B tree. Okay, I don't know where that is. But anyway, I had an earlier Python B tree that's also worth looking at, I guess. How people implement create graphs and random graph data to pass through things. So for random graph data, let me introduce you to the Stanford graph base. I don't know, there's probably something more modern. This is one of these crazy distraction books that Knuth wrote in the process of doing other things, and which were made in themselves a result of trying to do other things, etc. Like, he's like the ultimate yak shaver. But this is a book he wrote in preparation for, I guess, volume 4 of The Art of Computer Programming, which has a lot of stuff about graph algorithms. And actually, if you read the most, I guess 4A is the most recent volume. Maybe 4B is out now. But I would recommend reading the part of 4A that's about BDDs, which is, I learned of from, well, definitely not behavior-driven development, binary decision diagrams, and also CDDs. But yeah, you guys should check out the, volume 4, I guess volume 4A. About BDDs and CDDs, which are a really cool data structure for doing certain kinds of counting problems of combinatorial nature that are worst case exponential time, the way you'd expect for a lot of these problems based on their complexity class, but that are often much faster for natural problems. But anyway, for that and other work, he created the standard graph-based thing, which is a bunch of programs for generating parametrically a bunch of different example graphs. So like, I mean, if you want counterexamples for various kinds of graph things, there's also classical things like the Peterson graph, which is like a standard counterexample in graph theory. But yeah, check this out. There may be something more modern that's more convenient, but I think he has a bunch of stuff you can download if you want to get some graph sample data. In terms of how to implement and create graphs, I mean, the graph, like a graph is just a pointer structure, so all the usual techniques for representing pointer structures kind of apply. But I would say that don't actually use pointers, and maybe I shouldn't have said pointer structures, but like reference structures. So rather than using pointers anyway directly, you can do stuff like the graph itself has an array of things, and then vertices are represented indices into that array rather than having pointers directly. So you can do stuff like that. And of course, the standard representation split is between adjacency matrices and adjacency lists. And that's essentially, like we were talking earlier about tries, about how you sometimes want to have different physical representations of the same sort of semantic data. And that's a classic example of that, because adjacency matrices, at least when you're doing implementation rather than just math, an adjacency matrix is it's kind of like a bitmap for representing occupancy, is that it's pretty good when you expect about half of the nodes, well, in a bitmap you expect around half of the elements to be set and unset, so there's an even split. In the graph case, you expect, I guess, around half of the node graph pairs to be connected, not just connected, but immediately adjacent. And so adjacency matrices are great if you have graphs with a lot of density, a lot of connectivity directly to each other. Adjacency lists are great when things are sparse, and generally speaking, graphs are sparse. So I think people usually use adjacency lists unless it's some very specific use case. The array technique for linked lists, do you mean chunked linked lists? Like, for example, a cache line per chunk, and then you link the chunks together with previous next pointers or whatever? Oh, the Stenfor site, actually, that's just to get the graph data if you want to have some example data for your programs, for your algorithms. I mean, honestly, most textbooks are, like, graphs are not difficult to implement if you just want a standard, non-fancy implementation. It's just pointer structures, like linked lists and things like that. And again, you can represent them in more compact, efficient ways, but the basic structure is straightforward. The array technique for linked lists, I almost never use that, honestly, Gary. The cases where I use linked lists are when you have embedded linked list pointers. An example would actually be, we were talking earlier about the B tree. You have an existing structure, and you want to sort of cache pointers to different elements for rapid access. Then you just embed pointers directly there. That's really the only case where I use linked lists. So just to show people what I'm talking about, if if you did something like this, this is essentially a linked list, right? But it's embedded. I think this is pretty much one of the few cases where linked lists are a huge win. And in this case, it doesn't really make sense to do chunking because the allocation granularity is based on the node. And so I guess you could, yeah, so you can't, because the things are not organized primarily around next and previous. Next or previous are what, like in a database setting, you would call like secondary indices. And so the data is organized around its primary organization, which is the node level. And maybe the allocation order for nodes can be sort of memory coherent, but it doesn't make sense to lay out, in this case, for example, it doesn't make sense to lay out the data to be possible to do chunking at this level. And I don't even think that's generally possible. But anyway, but that sort of embedded links is the only case I really use linked lists. And so, yeah. Skip list. Oh my God. We're really covering everything. Yeah, I think the B-tree section was at the beginning. It should be recorded. I always record locally. It's the worst case I can upload to YouTube. But yeah, chunked linked lists. I wonder if this... I wonder if I'm also betraying a confidence by posting this. Sucker Punch programming interview. Problem Q. Okay, it's on Blastdoor, which I think makes it fair game. Okay. They don't have the full problem description. Okay, they do have the full problem description, so then I don't feel bad. not copy correctly. Where was last door? I wonder if they have like copy and paste protection because they're worried about people stealing their interview questions. Okay, I guess we'll just read it here. But anyway, the wait, did I not? Wasn't that here a second ago? Okay, I'm actually, I think I'm high. Okay, so you guys can go check it out if you think this stuff is cool. This is an example of a contrived but pretty cool problem. Like I know several people who have brought this up independently. I have a coworker from Bungie who knew about this randomly. I mean, like all kinds of random people have somehow happened across this interview question because I think it used to be on Sucker Punch's website, even for their gameplay programming positions. But anyway, so this is a problem to manage a variable number of byte queues. So the operand thing here is byte queue. It means that the payload per element in the queue is extremely low. So if you use linked lists to represent the queues, then you have 1 byte of payload, but you know, let's see, and you need 2 pointers, both previous and next pointers. And so if you're using pointers to represent this, and it's like, I don't know, that's like on the 32-bit, that's like 8 bytes just for the pointers and 1 byte of payload. That's a terrible ratio. They also have specific memory requirements, like they have only 2K of memory, and they have some, you know, you need to be able to handle single queues that are really big, but also an average, like a bunch of different queues that each only have a certain amount of bytes. So there's a bunch of different stuff here. Anyway, if you really analyze what's possible in these within these restrictions, given the requirements, you find out that you use chunked linked lists is the trick, basically, or at least the best trick that I came up with, which is that you know, you do something like a queue chunk is a has a certain number of bytes, and this is like the payload, and then you need within the chunk, I guess well, first off, you have like you have next and previous chunk pointers. So these are like, or not they're pointers, but they're indices because they're off. You know, there's only a certain number of chunks total. You're doing sort of free list style management of the chunks, and this is the chunk index. But then also, you know, some of these nodes can be partially full, and if they're partially full, they're either the head or the tail node, and so you also need to store like, I guess you need like a header that stores like, you know, there's a head chunk and a tail chunk. And you need to have like head size, tail size to figure out, you know, for the head, there's going to be some, let's see, for the head, there's going to be a suffix of the payload is going to be used, and size says how much of it. For the tail, a prefix of that storage is going to be used. And so you do something like this, and you turn the crank and work out the details, and lo and behold, you can actually meet the restrictions. So this is basically a chunked linked list data structure. Anyway, something like that. All right, let me just go back. I don't feel bad talking very loosely about the solution to this, just because, you know, I don't think job applicants will be able to find random Twitch streams that no one watches. So, all right, let me see. Bunch of triangulation algorithms. Triangulation is the devil. Just ask Sean. Ask Sean about fisting. or is it called fisting? Is the algorithm called fisting, or is it just fist? I can't remember. But whoever implemented that got fisted all right. Let me put it that way. That was triangulation is not good. That's a painful thing to get robust. Skip lists. Yeah, fist. Fast industrial, yeah. They don't mince words. The funny thing, well, I don't know if it's funny. I guess it's typical, but I remember reading the paper after Sean told me about it. I think he used a variant of that algorithm for Iggy 1, and the guy makes, I mean, I think an understandable and justifiable point about how most triangulation papers don't really cover the hard stuff, which is like how do you handle all the weird degeneracies and stuff like that. And but I guess the punchline is that Sean ran into a whole bunch of issues with Fist. So yeah, don't. It would be nice if someone actually came up with the real Fist, like the actual. Ideally, also, fists, maybe fists, like where the final S stands for simple or something like that, simple or simplified. Fists, fast industrial strength triangulation simplified. That would be nice. Oh yeah, skip lists. I've never found a good use for skip lists. I'm trying to remember. There's some really beautiful applications of it, but as a replacement for standard sort of search tree stuff, I never really. There's also treeps which have that same have that same reliance on randomization. Um, and that's another really simple case. Oh, speaking of treeps, do you guys know about priority search trees, which is an ancient computational geometry algorithm? So, which are actually essentially what treeps are. So I've talked before about how tries essentially have this data-independent subdivision of the search space, and that's what makes them simple. Priority search trees, so if you remember, treeps have two pieces of data per node. They have the sorting key, and they also have what they call the priority. Well, I can't remember what they're called in treeps, but they're called priorities in priority search trees. And it's basically like a heap key. So it has that restriction that the parent must be greater than or equal to the children's priority. And so it's a much looser invariant than the key ordering invariant. And it turns out that if you generate a normal sort of dumb unbalanced binary search tree, but you generate, each time you insert a node, you generate a random key for the priority, and then you do simple sift up, like you do the standard heap sifting on that priority key while maintaining the key ordering. You get some sort of probabilistic balance guarantee, which is data independent. So it's not randomized with respect to the key distribution. It's randomized with respect to the randomly generated priority. But anyway, for treeps, the priority is essentially just a piece of auxiliary data that's used to achieve some sort of probabilistic balance. But priority search trees are actually a way that you can have your own priorities in the game as well. And it does this by essentially, like, see if I'm not going to go through this. I don't even remember exactly. But my recollection is that in this case, they use both X and Y as sorting keys, or as keys. And I think the rough idea is that you do a normal binary search tree on one of the keys, and then you do a try on the other. And because the try is sort of data independent, it works out. So for example, you can use a whatchamacallit? You can use suppose you have a bounded box that contains all your geometry. If you're doing this in a computational geometry setting, you can use a fixed subdivision like an octree. Well, I guess it's not an octree. It's the equivalent of an octree for a quad tree, I guess. So you have that fixed subdivision that's data independent. But then within each section, you then do binary search trees on the other axis or something like that. My Twitter handle is I can't actually post here because I'm in incognito mode and I use LastPass, and so without compromising the whole idea of using incognito, I can't get my password from my password manager over here. So anyway, it's Per Vonsen, Pervoggnsen. That's my Twitter handle. Okay, Alex was asking about something. Maybe I missed the beginning. An eventually consistent distributed setup. Yeah, that definitely makes sense. The case when I mentioned earlier that skip lists have cool applications, the stuff I was thinking about was actually like consistent hashing and stuff like that. Like things that require less coordination, basically. Like normal balanced search trees have these coordination issues where if the nodes represent different machines that have to coordinate, it becomes a problem. But I think with this sort of thing, you can there's less coordination, I guess. I don't actually remember the details. Although, while we're talking about consistent hashing. And also Eric Veach. So here's a double tie-in, gentlemen. Eric Veach, jump hashing. I don't know if you've read this paper. Why is this co-authored by Veach? Oh, it is. I'm not going to go over it, but there's a very nice algorithm that's very small, which handles the fact that when you it's a pseudo-random way of when you add new nodes to the hash ring of like a distributed system or whatever. You want to basically divide an existing key range in half on average, but you don't want to do it by sort of coordinating. You want to handle it with like random people coming and leaving and stuff, and so you don't do it by sort of a priori dividing things down. It's a little bit like a load discrepancy sequence where you want that as more of a probabilistic thing. And they have a very nice sort of conceptual development where they start with a simple idea about how they basically use a simple random number generator, but then blah blah blah, and make it fast, and then they end up with this like super tight algorithm. But you guys should check this one out. And this is like a double consistent hashing and Eric Veach tie-in because Fabian mentioned Eric Veach in connection with the glue tessellator. All right, I should probably close down. Otherwise, I'm just gonna this is pretty much when I get into a tailspin about talking about random shit. This is what I sound like. So I think I'm going to finish up now. Anyway, thanks guys for hanging out. Maybe I'll try to do more of these. It seems to get more viewers than me just like writing random code live, which admittedly is not very action-packed. So this is maybe a little more interesting for people. I definitely have a lot of random shit I can talk about if people care. But anyway, thanks for coming by.